Bismillahirrahmanirrahim. Assalamu alaikum, students. So let us start today's lecture. Today's lecture is in continuation with last lecture. So let me write. It is Liouville's theorem. I will write continued. So we are continuing with the ideas which we established in the last two lectures. So I need some equations which we have labeled or numbered in the previous two lectures. First, we labeled Hamilton's equations of motion. Let me write those equations. Qi dot as dou h by dou pi, then time derivative of pi dot is minus times dou h by dou qi. We named these equations in the previous lectures as A, right? So we named these equations A. Let me write it neatly here. So these equations were A, which is the Hamiltonian of the system that you know that we have discussed already. Then in this connection, we wrote an equation for the, let me change the color. Let me use red here. For the partial derivative of rho with time, what was that? Dou rho by dou t is minus summation I is equal to 1 to f. F is the number of degrees of freedom in the system. Then dou by dou qi dot, no, it was rho qi dot plus dou by dou pi of rho pi dot. This equation we name it as 1. So this is the partial derivative of density function pertaining to some ensemble of systems, minus summation I equal to f, I is equal to 1 to f, dou by dou qi, rho qi dot plus dou by dou pi of rho pi dot. Then we wrote another equation, which was equation 2. I will use colors to distinguish these equations. Now I will use this one. What was the next equation? My next equation was this: dou rho by dou t is equal to minus summation I is equal to 1 to f. Then I have dou rho by dou qi, dou rho by dou qi times qi dot plus dou rho by dou pi dot Then there is another term in this sum, that is rho times dou by dou qi dot plus dou by dou pi dot. This whole thing is in the square bracket. We have named this equation as equation second, which is minus summation I to f dou rho by dou qi dot plus dou rho by dou pi dot plus rho times dou by dou qi of qi dot plus dou by dou pi of pi dot. As we have discussed, we obtain it to by using product rule of differentiation in equation 1. Then we wrote another equation, that was this equation which I named as 3. That equation was dou by dou qi dot plus dou by dou pi dot, which is equal to dou 2h by dou qi dou pi minus dou 2h by dou pi dou qi, and this we establish it as equal to 0. This we name it as equation 3. The last lectures, dou by dou qi of qi dot plus dou by dou pi of pi dot is equal to dou 2h by dou qi dou pi minus dou 2h by dou qi dou pi. Actually, what we did, we used Hamilton's equations of motion. Then we wrote it equal to 0 because the Hamiltonian is a state function. Then we wrote another equation 4. How we are getting these equations, I have already discussed in the previous lectures. I'm just listing these equations in order to move forward. I wrote another equation, dou rho by dou t equal minus times summation I is equal to 1 to f. Inside the sum, what we have, dou rho by dou qi dot plus dou rho by dou pi, sorry, it is p, let me clear it, dou rho by dou pi dot. We named it equation 4. This is the partial derivative of rho with time, which is one of the forms of Liouville's theorem, which gives us the rate of change of rho with time at a fixed point in phase space. There is minus summation I to f dou rho by dou qi dot plus dou rho by dou pi dot. Then we wrote another equation, another form of Liouville's theorem, which is in the form of double derivative, sorry, not double derivative, total derivative of rho with time. What was that equation? That is d rho by dt equal to dou rho by dou t plus summation I is equal to 1 to f, then I have in the bracket in the sum dou rho by dou qi dot plus dou rho by dou pi dot, and we established that this total derivative of rho with time is 0. We named this equation as equation 5. d rho by dt is equal to dou rho by dou t plus summation I is equal to 1 to f dou rho by dou qi dot plus dou rho by dou pi dot. And this is another form or version of Liouville's theorem, which gives us the rate of change of rho if one moves along in phase space with the point representing a system. Then we wrote another equation. Let me move to that. My equation 6. My equation 6 was about the partial derivative of rho with time, dou rho by dou t, which I wrote in this form. I've already established it, how it comes about. Summation I is equal to 1 to f. F is the number of degrees of freedom in the system. Dou rho by dou qi, dou h by dou pi minus dou rho by dou pi, dou h by dou qi. We named this equation as equation 6. Summation minus times summation I is equal to 1 to f dou rho by dou qi times dou h by dou pi minus dou rho by dou pi dou h by dou qi. H is the Hamiltonian of the system, as you know. Then what we did, we used the definition of the Poisson bracket of two functions, and we wrote another equation. Let me use this color now here. What was that equation? That was dou rho by dou t. Sometimes we write it this way. Subscript q comma p, that means point is fixed. Qp is not changing with time, as the negative of the Poisson bracket of the two functions, rho and h. This is the compact way of writing this, as we already discussed. We named it equation 7. I've listed all the equations which we have established. So let us move now forward. See, with the help of equation 5, we can obtain another form for Liouville's theorem, which sometimes is useful in certain situations. For this purpose, let us consider a region in phase space. I will use another color now. So let me use black. The point is, now let us consider a region of phase space. Some region, some volume. I write that as delta V, which I write as a multiple integral of dq. Let me set my pen. It is dq1 up to dpf. This is my equation 8. What is delta V? Delta V is some region in phase space. We are taking this region as small enough so that the density rho can be regarded as uniform over this region or extension. Repeat. So we take it small enough so that density rho is constant or can be regarded as constant or uniform over its extension over this region or over its extension. That is one and the same thing. Now I want to find the number of representative points inside this region. Therefore, number of representative points, each representative point is one of the system in the ensemble of the systems. So number of representative points inside this region let that be delta n. That delta n is simply rho density times the volume of the region, which is rho. Then we have this multiple integral dq1 up dpf. I made equation 9. Right? Rho delta v, rho times this multiple integral. Now, let us follow the motion of this little region through the phase space. Little region, that means this delta v. Want to see what will happen to this region as time evolves. You know, as time evolves, the points in this region will move according to Hamilton's equations of motion. Now, what will happen with this region delta V, this small volume region, as time proceeds, time evolves, right? And remember here, the boundaries of this volume of this region are the representative points lying in the region. I repeat, the boundaries of this region are also formed by the points within the region. Each point is representing some system in the ensemble lying in this region, right? So I want to see or find with time what will happen to the number of systems lying in this region delta V whose boundaries are also representative points lying in the region. That means I have to find the time derivative of this delta n. So delta n is rho dv delta V. So from product rule, it will be time derivative of rho times delta V plus rho times time derivative of delta V. Right? Now, d by dt of delta n must be 0. Let me name it equation 10. I am saying d by dt of delta n must be equal to 0. Why? I am saying number of points in the region delta V cannot change with time. Why it cannot change with time? I will give you two reasons. You need to think about those reasons. One is no representative points can be created or destroyed within this region. If some representative points can be created within the region, then this delta n will increase with time. If some representative points can be destroyed in this region, then delta n will be negative. Change in delta n will be negative then, but you cannot create any number of point or destroy the number of points existing in this region. So this cannot change due to that reason. Another reason is no points can cross the boundary and enter, or no points can cross the boundary of this region and leave the region. That can be the cause of change in delta n with time, but that cannot happen. Why that cannot happen? Because if some point leaves the region, that it has to cross the boundary, and boundary is formed by the points in the region. Why it cannot cross? That you need to think at home. Why no point can enter the region and cross the boundary? That cannot happen. Also, no point can leave the region and cross the boundary. No point can enter the region and cross the boundary. You think about that. That's your home assignment. So point is now that this delta n is conserved in time, so its derivative with time is 0. Now this derivative has two terms. Using equation 5, that is the Liouville's theorem, using equation 5, we already know the total derivative of rho with time is 0. So first term is 0, as we know from equation 5. This is my equation 5. We have already established it. So first term is 0. That means for d by dt of delta n to be 0, now second term has to be 0. Now in second term, you have rho and this derivative of delta v by delta v, this derivative of delta v with time. Now rho cannot be 0 because we are discussing the situation of some ensemble. It has some rho, non-zero rho. Then there is only one option. What is that option? I will write that in red. Implies that d by dt of delta v is equal to 0. Let me name it 11. Or you can write this in the integral form, your delta v, that is d by dt of this multiple integral dq1, dq2 up to dpf is equal to 0. So this equation 11 says what? It says the volume which you had considered in the first place will not change with time. Will not change with time. But what will happen with time? This volume, the points in the volume can move in time to different regions of the phase space. That will distort the shape of the volume. But the volume is not going to change with time. So if you take some infinitesimal volume, now we can build on this and use this result for any volume, because any volume we can construct by adding little infinitesimal volumes and create some volume. So this equation 11 is then telling you, if you consider some volume in phase space, now the boundaries of this volume are also your representative points. Now what will happen to this volume as it evolves in time? That means as time proceeds, the points in this volume will move according to Hamilton's equations of volume, but this volume is not going to change with time. So this shape of this volume may distort with time, but it will conserve the volume of the region. It may, on one side, its boundary may come out and enlarge, but it will adjust on some other side or some multiple sides in order to make the conservation of this volume happen in time. Now, this is also the form of Liouville's theorem. This equation 11 is also the form of Liouville's theorem, which is called principle of conservation of extension in phase space. I will use some color, another color, and name it. So this equation 11 is another version of Liouville's theorem. It is called principle of conservation of extension in phase. That means if you select some volume in the phase space and follow it in time, its volume will stay constant in time. Its shape may get distorted with time, but the volume will not change. So now we have completed our Liouville's theorem. I will summarize it. So we express now this Liouville's theorem in three ways. One is its partial derivative equation 4, which we then wrote in the form of a Poisson bracket of rho and Hamiltonian. Another form is its total derivative. What is the difference between partial and total derivative? In partial derivative, you are talking about the rate of change of rho with time at a fixed point. In total derivative, you are moving with the phase point and seeing how rho changes with time. So in 5, you are this as we already said, that this is the principle of conservation of density in phase space, that if I move with some point in the phase space, right, in the neighborhood, I will not find any change in the density of points, right? Now we have established another form, which is principle of conservation of extension in phase space. Let me write here space also. We says that if I consider some extension, some volume element in the phase space, boundaries are formed by the points in the region, then this volume will stay conserved in time. Its shape may distort with time, but its volume is not going to change. So we have completed this Liouville's theorem. Now I will give you a simple homework assignment. Your homework is this question. Question goes like this. A particle of mass m is free to move in one dimension denote its position coordinate by x and its momentum by p and its momentum by p. Change the color. Suppose that this particle is confined that this particle is confined within a box so as to be located between x is equal to 0 and x is equal to L, and suppose that its energy is known to lie between E and E plus delta E. Let me change the page. Draw the classical phase space of this particle indicating the regions indicating the regions of this space which are accessible to the particle. This is the question. Let me repeat it and check it. A particle of mass m is free to move in one dimension. Denote its position coordinate by x and its momentum by p. Suppose that this particle is confined within a box so as to be located between x is equal to 0 and x is equal to L. And suppose that its energy is known to lie between E and E plus delta E. Then draw the classical phase space of this particle, indicating the regions of this space which are accessible to the particle. So do this as at home. This all for today. Do not forget to like, share, and subscribe my channel. If you have any queries, you can comment on the YouTube. I will try to answer your queries. Thanks. Assalamu alaikum. Good luck.